Hey everyone. So today we begin chapter 1 in calculus on limits, and our first lesson here is just on one-sided limit. So it's kind of introducing the concept of what a limit is, and we're going to then take a look at trying to find that limit when we either come from the left or when we come from the right. Okay, so to start with, I want you to think about this scenario. A parking garage is charging the following prices: $3 for the first 2 hours, $6 for the next 2 hours, and $9 for any time after that. The piecewise function for this scenario would be this: f of t is the name of our function, and we say 3 if t is for time, is between 0 and 2. So it has to be, I want you to really look at the symbols here. It has to be greater than 0, and then it ends up having to be less than or equal to 2. Okay. Then once you're more than 2, you have to switch to 6. So it'll be 6 if you are greater than 2 and less than or equal to 4. And then you'd be 9 if you are greater than 4 and less than or equal to infinity. Okay, so I want you to try and draw this function. Now, I would really like it if you could do this on your own before I show you the picture. So I'm going to give you a few little hints here. It's 3 between 0 and 2. So if y is 3 between 0 and 2, you'd be looking at a horizontal line. Now, the difference is, though, you have to take into account whether you can equal the endpoint or not equal the endpoint. So I'm going to take you back to, I don't know, probably grade 9 when you started dealing with inequalities. And I want you to remember that when you can't equal the particular endpoint, you'd be an open circle. And when you can equal a particular endpoint, you'd be a closed circle. Okay, so think about that and see if you can draw it. Pause me for a second, draw your own, and then compare with mine. Okay, so mine to compare with would look like this. Okay, so I'm starting with an open circle at 0, and then I go until 2. Then I have at y equals 6, so that was y equals 3. Then at y equals 6, I start with an open circle at 2, because at 2, I'm actually being charged the 3, but then as soon as I'm more than 2, I start being charged 6. Okay, so then I'd have that line with a closed circle ending at x equals 4. And then at x equals 4, I'd also start with an open circle at 9. And then that would carry on for infinity. Okay, so then I don't have a closing to that line. Okay, so that's what my piecewise function looks like. Okay, now we're going to answer some questions based on that. So here's the first thing we're going to do, and this is the concept of a limit. Okay, as t approaches 2 from the left, the y values of f of t approach. So I'm going to approach 2 coming from the left. Okay, as I approach 2 coming from the left, the y values are approaching 3. Okay, and so we say the limit as t approaches 2 from the left is 3. Okay, so the limit refers to what number that scenario is approaching. Okay, now written mathematically, a limit would look like this. Okay, and how we say that is we say the limit of f of t as t approaches 2 from the left. You see that little negative sign? That means from the left, okay? And it's a superscript on the 2, okay? So the limit of f of t as t approaches 2 from the left equals 3, okay? Part of this is just getting the lingo down, okay? It's not actually super complicated what we're doing, but you really need to nail the communication. Okay, so the limit of f of t as t approaches 2 from the left is 3. Okay, now let me just take that arrow off too. So as t approaches 2 from the right, the y values of f of t approach. Okay, so as t approaches 2 from the right, the y values actually approach 6, okay? Because coming from the right, there is nothing here. Coming from the right, we'd have to be on this guy. So as we approach from the right, the y values are approaching 6. we say the limit as t approaches 2 from the right is 6. Okay, and then again, written mathematically, same thing. The only thing that's going to be different is that 2 to the negative sign is going to be 2 to the positive sign, okay? Because that means we're going to come from the right instead of coming from the left. So it'll be the limit of f of t as t approaches 2 from the right. That's what that little positive sign here is talking about, okay, is 6. Okay? Okay. Notice that these are two limits that approach the same x value but different y values. Okay, so now determine the following. So we're going to look at the limit of f of t as t approaches 4 from the right is the first one, and as t approaches 4 from the left. So if I'm approaching 4 from the right, okay, from the right, I would be looking at 9. Okay, from the left, which is that negative sign, I would be looking at 6. Okay, so this guy is from the left, and this guy would be from the right. Okay, so you're kind of following on the function that you've got in the direction you're asked to go. Okay, good. Okay, would you describe this graph as continuous or discontinuous? Well, let me remind you of the definition of continuous and discontinuous. Essentially, continuous means you can, like, this is not a calculus definition, but essentially, continuous means you can draw the whole thing without lifting your pencil. You cannot draw the whole thing without lifting your pencil here. There is discontinuity in this graph, and so it is discontinuous. So the graph is discontinuous. You have to lift your pencil to draw, okay? Okay. In general, the left-hand limit of f of x as x approaches a from the left is written like this, okay? The limit of f of x as x approaches a from the left. Each one of those symbols means something, right? The arrow is approaches, that negative sign tells you you're coming from the left. So as x approaches a from the left, that describes the limit of f of x. The right-hand limit of f of x as x approaches a from the right looks like this. The only difference is we've got that plus sign there instead of the negative sign, okay? Okay, so consider the following. The limit of f of x as x approaches -1 from the left. So here I am approaching -1 from the left. My y value is approaching 0, okay? Okay, now what if I need to approach it from the right? Here I am approaching from the right. My y value is approaching 0 still. Okay, is this graph continuous or discontinuous? Can you draw it without lifting your pencil? The answer to that is yes. So it is continuous. And then f of -1, well, actually f of -1 is 0. So here's an example. I'm going to get to this in a minute, but here's an example that the limit on the left equals the limit on the right and equals f of -1. Okay, they're all the same number. Spoiler alert, that speaks of continuity, okay? But we'll get there. Okay, consider the following. Let me take off the arrows from the previous drawing that I made. Okay, consider the limit of f of x as x approaches 2 from the left. So as x approaches 2 from the left, y is approaching 3. So the limit is 3. Okay, as x approaches 2 from the right, y approaches 5. So the limit there would be 5. I'm not sure if you can see that last arrow I drew from the right because I think my head might be in the way. So I'm just going to clear my head for a sec. Clear my head, get it? I need to think a little clearer. Okay, so just so you can see, this is me approaching 2 from the right. Okay, I've cleared my head, I'm coming back. Okay, was this continuous or discontinuous? It is discontinuous. There's a big gaping hole in that graph. I cannot draw this graph without lifting my pencil, okay? And then what does f of 2 equal? In this instance, look for the circle that's colored in. f of 2 is 5. Okay. Okay, so this speaks of discontinuity because the limit on the left does not equal the limit on the right. Okay, they were two different numbers. As soon as the limit on the left does not equal the limit on the right, there must be some sort of a gap or a hole there. Okay. Okay, consider the following. The limit as x approaches -2 from the left. Okay, I'm going to clear my head again for a sec just to make sure you can see this. So as x approaches 2 from the left, here I go, I'm approaching 4. As x, okay, let me just put that up there for, whoops, let me just put that up there for a sec. Okay, as x approaches 2 from the right, I'm approaching 4. So here we get really excited and say, huh, the limit on the left equals the limit on the right. So now my next question is, I gotta put myself back here for a second. My next question is, sorry, I couldn't figure out how to put myself back. Okay, my next question is this continuous or discontinuous? It is actually discontinuous because of that point of discontinuity, okay? Now, last slide, I said, hey, the limit on the left doesn't equal the limit on the right, so this graph is discontinuous. Well, now this is interesting because the limit on the left does equal the limit on the right, and I'm still saying this graph is discontinuous. And here's why. What's f of 2? F of 2 doesn't exist because it's a point of discontinuity. Okay, so I was leading you up to this conversation, and it's not just the limit on the left has to equal the limit on the right. The limit on the left has to equal the limit on the right, which also has to equal f of whatever that is, okay? You need to have that trifecta. If all three are there, then you have a continuous graph. If one of those is not the same, then you have a discontinuous graph, okay? Okay, so consider the following. Let's look at, I'm gonna clear my head. The limit of f of x as x approaches 0 from the left. So as I'm approaching 0 from the left, what's happening to y? Well, y is actually shooting down to -infinity, okay? What is happening as I approach 0 from the right? Well, y is shooting down to -infinity. Okay, so both of those guys are -infinity. Okay, I'm just going to bring myself back. Is this graph continuous or discontinuous? It is discontinuous because I have a vertical asymptote there. You can visibly see that. Some of you may look at that and say, well, how do I know they don't connect really, really steeply at the bottom somehow? They don't. That's kind of impossible the way this graph looks. But so that you're not stressed out about that, I would say if that ever existed, we would have to show you that, okay? So if you see these guys shooting down like that, you assume that they're shooting down because they're heading towards a vertical asymptote, not that they're heading towards each other, okay? So it is discontinuous, and f of 0, what's f of 0? Again, it doesn't exist because that's a vertical asymptote. So again, you don't have the trifecta, and that's why it's discontinuous. Although the limit on the left does equal the limit on the right, it does not equal f of the number in question. Okay, you have to have all three happen in order to have a continuous moment. Okay, and so here is the definition of continuity that I have been already saying. If the limit of f of x as x approaches a from the left equals the limit of f of x as x approaches a from the right, which equals f of a, then f of x is continuous at the point A. If one of those doesn't happen, so if the limit on the left doesn't equal the limit on the right, I'm now paraphrasing the green that you're looking at there. If the limit on the left does not equal the limit on the right, or the limit on the left does equal the limit on the right, but they don't equal f of a, so you don't have the trifecta, then f of x is discontinuous at a, okay? That is the definition of continuity from a calculus perspective. Okay, so informally, a continuous function has no breaks or holes, and discontinuities occur when there are breaks or holes in the graph. Okay, all right, so now for g of x, if g of x is going to be x minus 1 when x is less than 0, and it's going to be x squared when x is greater than or equal to 0. Determine the following limits, if they exist, then try to sketch the graph. Well, sketching the graph won't be hard, but let's actually try and figure out the limits first. So as x approaches 0 from the left, well, as x approaches 0 from the left, I have to be less than 0, so I would need to be looking at x minus 1. If I plug in 0 into this equation, I get out -1. So that means I must be approaching -1. Okay, as x approaches 0 from the right, well, I have to be coming from the right, which means I have to be coming from a greater than 0 standpoint, which means I'd be looking at this piece of my piecewise function. And so I plug 0 in there. 0 squared is 0. Okay, so the limit as x approaches 0 from the left is -1. The limit as x approaches 0 from the right is 0. Right away, you're going to tell me this is not continuous at 0, because these are not the same number. The limit on the left does not equal the limit on the right. Okay, now in order to draw these, what I do is I draw the line x minus 1 up until x is at 0, and then I draw an x squared graph up until, or I guess not up until, because I'm reading left to right, I should say from 0 on. So just as a quick sketch so that you understand what I'm about to do, because I'm going to show it to you like the cooking show and it's all going to be done for you. So the line x equals 1, 2, 3, 1, 2, 3, 4, 1, 2, 3, 4. Now don't do what I'm about to do. I just want to paint the right picture for you. So the line x minus 1, well, that starts at -1, and I'm going to go down 1 over 1, down 1 over 1. Okay, so it's that line there. Okay. Okay, well, I'm going to draw that line. I'm going to take a nice ruler, but I'm only going to draw it up to 0. And I can't actually be x equals 0, because at x equals 0, I'm the other function, right? It's the x squared gets your greater than or equal to 0. So I'm actually going to erase that point and put an open circle there. And then this is going to be my graph. This is x minus 1 up to 0. Okay. Then the other guy is a parabola. X squared would look something like this, right? I'd have the point 0, 0. I'd have the point 1, 1. I'd have the point 2, 4. 1, 2, 3, 4. Okay. Now I'd have that whole parabola, but I don't care about it over here because it says I only want it when x is greater than 0. And so I'm looking at this. Okay. And that is the graph that's described by this piecewise function. Okay. So now I'm going to put on the actual graph, and you can see, hey, I did pretty good. Okay. Hopefully you did the same. All right. Let's try this one now. Draw the graph of f of t equals t minus 2 over t squared plus t minus 6 on the domain -5 to 5. So we are drawing this graph, but we're only drawing this graph between -5 and 5. You'll notice I have square brackets there, so I can be the endpoints. I can be at -5 and I can be at 5. Be sure to label all asymptotes, points of discontinuity, and endpoints, then determine the following limits. Well, this is just a trip down memory lane for 30-1ers. We're going to factor this, and then once we factor it, we'll be able to figure out where our asymptotes are, where our points of discontinuity is, all of that jazz. So go ahead and factor it first. Okay, and so the bottom factors into x minus 2 times, sorry, t minus 2 times t plus 3. Okay, so right away, I have a point of discontinuity at t minus 2, so that's at t equals 2. Now, we have trained you so well in 30-1 to say what the physical point is, right? So the physical point, this would be f of, sorry, that's a little typo there. That should say f of t. F of t equals 1 over t plus 3, but we know that t can't be 2, and so if I plug in 2, I get 1 over 5. So I know I have a point of discontinuity at 2, 1 over 5. Now, that's beautiful, and you do need to know where that point is, but when we're stating it, From a calculus perspective, points of discontinuity are just at the x value. They're not the actual point. And I know that's going to frustrate the heck out of you because in 30-1, we drilled you that points of discontinuity had to include the y value. In calculus, it's looked at from an x perspective. You need to know the y value in order to draw it properly. But when you're communicating it, you just say point of discontinuity at x equals 2. Okay, so I have a point of discontinuity at x equals 2. I also have a vertical asymptote at, sorry, I shouldn't have said x there. I should have said t. I just listened to myself. I need to listen to myself a little bit more often. Okay, so t equals 2. I have a vertical asymptote at t equals -3. I don't have an x-intercept because I don't have a factor on the top by itself. I have a y-intercept. I could plug in 0 for t and I'd get out 1/3. So I know I have a y-intercept at 0, 1/3. For this one, in order to draw an accurate graph, I also need to know my endpoints. So I need to plug in -5 and I need to plug in 5. Okay, if I plugged in -5, I would get out -1/2. So -5, -1/2. And then +5, 1/8. Again, I'm just plugging those values in for t. Okay, so I have a point of discontinuity at t equals 2. Then I've got a horizontal asymptote at y equals 0. Now, for now, we can approach the horizontal asymptote just like we did with in 30-1. This gives me a smaller degree over a larger degree. And whenever I have small over big, the horizontal asymptote is at y equals 0. In a little while, I'm going to teach you how to find horizontal asymptotes from a calculus perspective, but for now that will do. We've got the vertical asymptote at t equals -3, and then we have our endpoints at -5, -1/2, and 5, 1/8. Okay? So the only thing I hadn't talked about there was the horizontal asymptote. Okay, now we're going to try and draw it. So again, remember, I need to start with my endpoints. I'm not going to draw this whole thing. I'm only going to draw from -5 to 5. And I can be -5 and I can be 5. So those will start with colored in dots. Okay, so your graph should look something like this, where I start at -5. I've got my vertical asymptote here at x equals or t, I guess, equals -3. I've made sure I threw in my point of discontinuity at 2, 1/5. And then I also have my 5, 1/8 as my endpoint there. Okay? Okay, so now we're going to determine the following limits. Determine the limit of f of t as t approaches 2 from the right. So I'm heading this way as t approaches 2 from the right. Let me draw that in just in case you didn't see my mouse do that. Okay, t approaches 2 from the right. I'll be heading towards that point of discontinuity, which would be at 1/5 because we're answering the y value there, right? Okay, as t approaches -3 from the right, so as t approaches -3 from the right, I just want to draw that in for you. I'd be going like that. Okay, so I would be approaching positive infinity. As t approaches 5 from the right, as t approaches 5 from the right, I'm over here. Okay, I don't exist on the right. As t approaches 2, so just for clarification there, I can't say I'm approaching something when I don't exist, okay? I have to be on the graph in order to approach something. That's why we say it doesn't exist there. Some of you are yelling at me at the moment and you're saying, yeah, but at 5, I exist. Yes, but to the right of 5, I don't exist because I've only gone to 5. And so I can't approach from the right because I don't exist from the right. In order to approach, you have to be riding along the function, okay? Okay, that was my little limit lecture. It was limitless. Huh. Okay, so as t approaches 2 from the left, so let me just, t approaches 2 from the left. Again, I'm approaching that point of discontinuity, which would be 1/5. As t approaches -3 from the left, so -3 from the left, I'm approaching negative infinity. And as t approaches -5 from the left, no, positive 5, sorry, as t approaches 5 from the left. This time I do exist because I have something I can ride along. Okay, so as I approach 5 from the left, I will be approaching 1/8 because that's where that endpoint is. Okay? Awesome. Okay, determine the limit of the following without graphing. To determine a limit without graphing, substitute values that are really close to the limit. So for instance, let's say I'm approaching 2 from the left. Well, if I'm approaching 2 from the left, I want to look at like 1.9 and 1.999 and 1.99999. That approaches 2 coming from the left. Think about it as a number line, okay? If I approach 2 coming from the right, I want to try maybe like 2.001 and 2.00001 and 2.00001, okay? That's approaching it from the right. I'm getting closer and closer to coming from the right, okay? Okay, so the limit as x approaches 2 from the right, can you think of what that would be? I would be approaching 0. Okay, for the next guy, the limit of the root of x as x approaches 0 from the right would also be 0. And the limit of sine of x as x approaches 0 from the left is 0. Sine of 0 is 0, right? Okay, in most of these guys, in all of these guys, you could just plug it in. But there will be opportunities where you can't plug it in because you get like a non-permissible value, and that's where you'd have to go, okay, well, let's try 1.9 and 1.99 or whatever, okay? All right, good job. So that's it. Your homework is there, and I would encourage you to, before our next class, kind of read through or watch the video too of the next section too, so that as you come in, you're prepared to go. Okay, thanks guys. See you soon.